Okay. So I shall be continuing my lecture uh, on some important aspects concerned with number theory. Although these concepts can be dealt with the theory of groups, because we are in the finite group ZP for a prime P. Okay. So let us start with the statement due to Fermat, that is, which is known as Fermat's theorem. Okay. So what is the statement? The statement is like that. Suppose P be a prime. Okay. And A belongs to Z. A be any integer. P be a prime and A be any integer. Then if you raise A to the power P, then you will see that this is going to be congruent with small a modulo P. So this is the statement, that A to the power P must be congruent with A modulo P. Okay, fine. So how to achieve this proof? Okay, so then to achieve this proof,
স্যার
hello,
স্যার অঙ্কিতা বলছে জয়েন হচ্ছে না আমার।
বলো বলো, আমি করে দিচ্ছি, জয়েন করে দিচ্ছি। হয়েছে হয়েছে, ওকে ওকে। আরে আচ্ছা, হাত লেগে আমার আমার জন্য হয়েছিল গো, সরি।
আচ্ছা আচ্ছা, না না, কোনো প্রবলেম নেই।
হ্যাঁ হ্যাঁ, okay. So to how to achieve this proof, the proof is like that. So first of all, you will see that a to the power p minus a, that can be written as, so taking out a outside this bracket, so it will be a to the power p minus 1 minus 1. Okay, so to show that a to the power p is congruent to a modulo p, that means your aim is to show that p divides a to the power p minus a. That means p divides this one. So our goal is p divides a to the power p minus 1 minus 1. Okay. Now, if p divides a, then we are done, right? Because in that case p will divide the whole integer, right? So then we are done. But for the other case, but suppose that P does not divide A. Okay, so P does not divide A. Then you must have to show that P divides A to the power P minus 1 minus 1. This quantity. Okay. Now, since P is a prime, since P is a prime and P does not divide A, then what would be the GCD of A and P? Then we can say that GCD of A comma P is 1. Since P is a prime and P does not divide A, so their GCD must be 1. This is a simple observation, right? Also, since P is a prime and if you consider Euler's phi function, then the image will be P minus 1, because there are, for a prime P, the number of integers that are less than P and prime to relatively prime to P is P minus 1, right? So phi P is P minus 1. Therefore, by virtue of Euler's theorem that we have proved in our last lecture, so what was the statement? Euler's theorem, the statement is like that. Suppose you have a positive integer n and yes, then for any A belongs to Z with GCD of A comma n is 1, you will going to have A to the power phi n is congruent to 1 modulo n, right? So this is the statement of Euler's theorem. Okay, so in that case, P be the positive integer and A is an integer for which GCD of A comma P is 1. So therefore, you can apply Euler's theorem in this context. So therefore, by virtue of Euler's theorem, we have, so A to the power phi of P is going to be congruent with 1 modulo P. But what is phi P? That is A to the power P minus 1 is congruent to 1 mod P, right? And this proves that P divides A to the power P minus 1 minus 1. And hence, P divides A multiplied by E to the power P minus 1 minus 1. That is, P divides A to the power P minus A. That means A to the power P is congruent to A modulo P in both the cases. And this proves that this completes the proof. Right? So this completes the proof. Okay. Okay. Now again, Let us move to some other aspects of finite groups, which is also a crucial counting principle whenever we are going to study advanced group theory. Then you will see that in finite groups, this counting principle will have some great impact. What is that? Okay. So now we are going to discuss on certain counting principles which will play an important role in the theory of finite groups. Okay. For instance, suppose G be a group. Suppose G be a group, A and B are subgroups of G. Then the set AB, denoted by AB, which is constituted by the elements of this type. A, B, A compose B, where A belongs to capital A and B belongs to capital B. Then this set need not be a subgroup unless AB equal to BA. That means AB is a subgroup. We have already proved this. If and only if AB is going to be BA. Okay. Okay. So it's a natural question that how could you yes. So how could you evaluate the number of elements in this set AB in terms of the number of elements in A and the number of elements in B in the context of finite subgroups? That means if A and B are finite, then what would be the number of elements of this AB? So the statement is like that. So let A, B be two finite subgroups of a group G. Okay. Then the cardinality of AB is equal to cardinality of A, cardinality of B divided by cardinality of A intersection B. Not only that, it's equal to the cardinality of BA. Okay. Okay. So this we can prove very easily, just having a look at the elements of AB, how they can be represented in terms of elements from this set. Okay. Suppose the proof starts with the fact that let A belongs to capital A, B belongs to capital B. Okay. And X belongs to A intersection B. Then just look at the product AB. Then you can represent AB as A X inverse X inverse B. Since X inverse is identity, so you can take this element in this product. Okay. Then by associativity, it is AX and it is X inverse B. Now, if you look at these two elements, you will see that this X, now X is in A intersection B. That means it is in A and B also, both. So for that reason, AX is an element of A, X inverse B is an element of B. So any element of AB, capital AB, it can be represented as another two elements of A and B by virtue of the elements of A intersection B. So how many times you can represent one element AB in terms of this representation? The number of elements of A intersection B will determine the number of representation of this element in terms of this. So how many times you can represent AB? Like the product of an element of A and an element of B, that is the number of elements of this set. And since A and B both are finite, so intersection B is also a finite set. Okay. Okay. Suppose conversely, let you are representing AB as another representation in terms of an element of A and an element of B. Suppose AB can be represented in another way with the help of an element of A and an element of B. Then using this representation you can have, so A1 inverse A will be B1 B inverse, right? So these two elements are equal, but this element is in A and this is in B. So that means this element is in A intersection B. And so let X is A inverse A or B1 B inverse, whatever take. And using this X, so therefore, so what is A1? What is A? A is A1X. And what is B? B is X inverse B1. Yes. Okay. So therefore, which says that so AB is actually A1X X inverse B1, right? So this is A1 B1. So hence, with the help of this, you can say that for A belongs to capital A, B belongs to capital B, the product AB, how many times does it appear? Appears cardinality of A intersection B times, right? The number of elements of A intersection B appears cardinality of A intersection B times as a product of A and as a product of A and B. Yes. So this implies that the number of elements of the product set AB equals the number in the listing of AB as a product of an element in A and an element in B. B, yeah, divided by so divided by which number? Divided by the number of times a given element appears. That is cardinality of A intersection B times, right? So hence the number of elements in the product is actually the number of elements in A product with B by cardinality of, because each element will appear cardinality of A intersection B times. So to get the unique one, so you need to divide this cardinality of A intersection B with cardinality of A intersection product cardinality of B, and this is actually equal to BA also. Yes, as A intersection B commutes with equals to A B intersection B. So that is the reason, right? Okay. Okay. To end up this session, I mean the discussion on these counting principles. So let us end with an exercise that I am going to give you as a home task. That okay. So recall that if H be a subgroup of a finite group G, then by means of Lagrange's theorem, the index is the order of G by order of H, right? Okay. So this much we can know from this Lagrange's theorem. So using this one, let us have an exercise. What is the exercise? Let A, B be two subgroups of a finite group G. Okay, of a finite group G. Then number one, if A subset of B, then you need to prove that the index of G colon A is equal to index of G colon B index of B colon A. Okay, this is the okay. Number two, index of A colon A intersection B. Now, since A and B are two subgroups, so their intersection is also a subgroup, and it is a subgroup of A and B both, right? But the index A colon A intersection B is always less or equal to the index G colon B. Also, number three, the index A colon A intersection B equals with the index G colon B if and only if G equals with AB. Okay, and the fourth one is very important. The index G colon A intersection B can be written as the index G colon A multiplied by index G colon B. But if and only if, whenever you can represent G as B. Okay, so each of them has some impact on finite groups. Okay, so this has been left as an exercise. এটা কিন্তু করো, ঠিক আছে, চেষ্টা করো, পারবে, জাস্ট ইউজিং ল্যাগ্রাঞ্জেস থিওরেম ওটাকে কাজে লাগিয়ে করতে হবে। এবং দ্যাট ওয়ান, this one, yes, this result, this is very important one. So using this counting theorem you can prove these four by means of Lagrange's theorem also. Okay. 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 Now we are moving to discuss on a very special kind of subgroups that has been emerged out in group theory to construct new groups. And not only that, we will see in advanced group theory in the extension of fields in postgraduate courses, you will see that these normal subgroups has very important impact on field theory also. Okay. Whenever we are going to deriving roots of equations, polynomial equations, then we will see that these normal subgroups has an important impact. Okay. Okay. So yeah. Okay, fine. So now we are going to discuss on some special kind of subgroups of a group G, okay, which has a great deal of impact in abstract algebra. Which had been cited by the mathematical wonder the great mathematician Evariste Galois. Right? Evariste Galois. He died at the age of 21. Okay, and in between his age from 16 to 21, he had proved a, some marvelous theorems in abstract algebra, which has been discussed in after 100 years of his death, I think. Yeah. Okay. So what are those normal subgroups? Yeah. So let us have a look at the following example. Okay. Let G is S3. What is S3? You know that it is constituted by these elements E phi psi square phi psi and psi into phi, where E is the identity permutation, phi is 1 2 cycle, psi is 1 2 3 cycle, right? And obviously phi psi is not equal to psi into phi. Phi square is identity, psi cube is identity. Okay. Let H equals to E psi psi square. So since order of psi is 3, so this psi will generate a cyclic subgroup of order 3, right? Okay. Now you need to find out the left cosets and right cosets of H in G. Okay. So what are the left cosets? First of all, the left cosets of H in G. Okay. So firstly, you will take EH, but EH is H. Then you need to take phi. So what is phi H? Phi H is phi psi, and phi psi square. Okay. Fine. Then you take pi into psi, which are outside H. So phi psi H. What are those? That means phi psi, phi psi square, and phi psi cube, right? So that means again, so phi psi cube is identity. So it is phi into psi, and it is phi psi square. That means it is again phi H equals with this, right? Another one is psi into phi. That means psi phi, psi phi psi, psi phi psi square. Now what is that? What is this? So if you check on your own that what is psi phi H, then what you will see? What you will see?
স্যার এটাও তো ফাই এইচই হবে।
কেন হলো তো?
কারণ স্যার সাইটা তো আইডেন্টিটি এলিমেন্ট হয়ে যাবে, সাই আর এটা দিয়ে তো ফাই এইচ হবে।
কোনটা আইডেন্টিটি হয়ে যাবে বলো?
মানে স্যার সাই ডট আর এদিকে ফাই ফাই সাই কমা ফাই সাই স্কয়ার দিয়ে স্যার ওটা তো আইডেন্টি হয়ে যাবে মানে সাইটা
এইটা 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 এইটা
আগেরটার মতো। হ্যাঁ
এইটা বলছি এটা।
হুম।
আর কিভাবে বলতে পারো একটু বুদ্ধি করে?
কিন্তু কিন্তু ওভাবে দেখতে গেলে স্যার ফাই ফাই আর সাই ফাই তো এক না, এটাকে তো একসঙ্গে লেখা যাবে নাকি স্যার?
না, এই দুটো এক নয় তো, এটা আলাদা।
স্যার না, আমি বলছি থার্ড টার্মটা যে স্যার সাই ফাই সাই স্কোয়ার, ওটাকে তো ফাই সাই কিউব করে আইডেন্টি করা যাবে না তো, মানে যেহেতু ফাই ফাই আর সাই ফাই এক নয়।
না, সেটা করা যাবে না, কিন্তু এইটা মানে কিন্তু এটা হতে পারে, মানে সাই ফাইটা ফাই সাই স্কয়ারের সঙ্গে সমান হতে পারে, পারে কিনা দেখো, সেটাই চেক করতে পারি। বুঝতে পারলে? আচ্ছা, এইটা কত হচ্ছে বলো, ফাই ইনভার্স সাই ফাই, এটা কত হচ্ছে বলো তো? এটা কত হচ্ছে? ফাই ফাই মানে কি? 1 2 3, ফাই হচ্ছে 1 2, তার মানে
টু
এইটা তার
ওয়ান
ইনভার্স,
থ্রি
আর এটা হচ্ছে 1 2 3, তার মানে 1 2 2 3 3 1, আবার হচ্ছে 1 2 3, তার মানে 2 1 3, তার মানে এটা হয়ে গেল, তার মানে এটা হচ্ছে তোমার ওই একই থাকছে 2 1 3, যেহেতু ওর অর্ডারটা, its order is 2. Okay, so then what you will get, okay, so 1 goes to 2, 2 goes to 3, 3 goes to 3, so 1 goes to 3, 2 goes to 1, 1 goes to 2, 2 goes to 1, it is 1, 3 goes to 3, 3 goes to 1, 1 goes to 2, so it is this. So that means it is, what is that? This is actually 1 3 2 cycle, right? That means, now what is psi square? What is psi square? Just check. That is 1 goes to 2, 2 goes to 3.
1 3 2 সাইকেলটাই স্যার।
Yes. So it is 1, it is 2. So that means it is 1 3 2. So that means it is phi inverse psi phi, right? So what does it mean? So phi inverse psi phi belongs to H, right? Now compare this fact with the condition of two left cosets are equal if and only if A inverse B belongs to H. This is your phi, so it is phi inverse, and B is phi psi phi. So this one. So phi inverse psi phi belongs to H means phi H equal to, okay? Is it clear?
Yes sir.
Without going to deduce all the permutations, we can achieve this with the help of the condition of two left cosets will be equal. Yes. So phi H is equal to psi phi H. So therefore, the left cosets are H phi H. Okay. Now, in a similar way, the right cosets are H and H phi. Okay, and this tells you that, so therefore for this subgroup, for this H, you see that the left cosets are equal to right cosets, right? For this H, the left cosets of H in S3 is equal to left cosets are equal to the right cosets of H in S3. Okay, but if you consider another subgroup, suppose K. What is K? K is E phi. So it is again a cyclic subgroup generated by phi, since the order of phi is 2. Now if you consider this subgroup, then you will see that then we have seen that, I think we have deduced all the left cosets and right cosets in our previous lectures of this subgroup. I think yes, or করেছিলাম না এটা, এর লেফট কোসেট গুলো বার করেছিলাম, রাইট কোসেট গুলো বার করেছিলাম, তো এই সাবগ্রুপটা দেখো তো, যখন লেফট কোসেট করেছি দেখো তো, we have seen that the left cosets of K in S3, seen that there exists a left coset of K in S3 which doesn't equal with any right coset of K in S3. That means in a group you have a subgroup which enjoys the property that the left cosets of that subgroup in S3 equals with the right cosets of H in S3, but at the same time you have an example of subgroup in S3 which doesn't enjoy this property. That is, there exists a left coset of K in S3 which does not equal with any right coset of K in S3. So this type of subgroups H, which has this special kind of property that their left cosets coincides with their right cosets of H in S3. So that are called normal subgroups. So the definition can be taken like that: a subgroup, okay, 1 minute. Yeah, so the definition is that a subgroup n of a group G is defined to be a normal subgroup in G if every left coset of n in G equals with a right coset of n in G. Okay, every left coset of n in G equals with the right coset of n in G. And if some subgroup of a group G enjoys this property, then that subgroup will be defined to be a normal subgroup. And it has some special kind of feature in abstract algebra. Okay. Now, note that the fact is that in the definition we have written that every left coset equals with the right coset. Okay, every left coset equals with a right coset. Yeah. So the fact is that, note that if a left coset, suppose n, if it happens to be a if it happens to be a right coset, then it must be NA. Okay, in our definition we have assumed that a subgroup is said to be normal if every left coset equals with a right coset. But I am not saying that every left coset n equals with NA. But what I am saying that every left coset equals with some right coset. That means n equals with some nx. So I am saying that n equals with some nx. I am not saying that n equals with na. But eventually you will get the result that if a left coset n happens to be some right coset, so that right coset will be na only. So that is the fact. Why? Because if it is some nx for some x, then what you will get? Then small a belongs to n, because you can represent a as a dot e. So that is why A will be in An. Now An is an X, right? So A in Nx means A X inverse belongs to N. By the relation that we have defined for right cosets. So Ax inverse belongs to N. And this implies that Na equals with Nx. So that means the right coset Nx coincides with Na. Okay. So that means if a left coset of N in G equals with the right coset, then that left coset will be the corresponding right coset of An, that is Na. Okay. So that is the crucial fact. Okay. Now we need to establish some equivalent statements for a subgroup to be normal. Okay. To be normal. So what are those? So the theorem is like that. So the following are equivalent. Okay. For a subgroup N of a group G. Number one is N is normal in G. So N is a normal subgroup in G. Number two, so we have the fact that every left coset equals with its corresponding right coset. Right. So there is not only that, for all A belongs to G, An A inverse will be a subset of N. Okay. Number four, every right coset of N in G is a left coset of N in G. Okay. That means if you start with right cosets, and if you are calculating the right cosets of N in G and then left cosets of N in G, and you will find that every right coset is equal to some left coset of N in G, then you can say that N is normal. Okay. Okay. Number five, the product. Product means we have already seen that if A is a set in a group, P is a set in a group, then you can define the product. B belongs to B, right? Okay. So the product of any two left cosets of N in G is also a left coset of N in G. Okay. Number six, So in a similar way, the product of two right cosets of n in G is also a right coset of n in G. An dot Bn equals to Abn for all a comma b belongs to G. Similarly, you can define 7 Na Nb. It will be Nab for all a comma b belongs to G. And the last one is yes. Yes. The set of all left cosets okay, yes, I don't want to introduce this one. Okay. Just you can, yes, for any two elements a comma b belongs to G, A inverse B belongs to N if and only if AB inverse belongs to N. That is to say that A is congruent to B L mod H if and only if A is congruent to B R mod H. If you remember, you can say that these are the binary relations that we have defined on the group G with respect to N. That is, if you take two elements A and B, then you have stated that A is congruent to B modulo H means A inverse B belongs to sorry, this is N. This is N. So A is congruent to B modulo N means A inverse B belongs to N for the case of left cosets. And you have defined also A is congruent to B modulo N if and only if AB inverse belongs to N, and that gives you right cosets, right? But for normal subgroups, you will see that these two are same. Whenever you are getting A is congruent to B modulo N with respect to left relation, then you will get that A is congruent to B modulo N with respect to right. And similar way, A is congruent to B modulo N with respect to the right relation will give you that A is congruent to B modulo N with respect to the left one for the normal subgroups. Okay. Okay. Yeah. So let us try to prove one by one. Now, according to 1 implies 2. What is that? So suppose N is normal. Okay. So 1 implies 2 means if N is normal, then An equal to Na. And that we have already proved. It has been proved. Right? 2 implies 3. So if An equal to Na, then if An equals to Na, then it is obvious that n A inverse is n, right? Okay. Now 3 implies 4. 3 implies 4. So suppose that n A inverse is a subset of n for all A belongs to G. That is a condition of 3 to be 2. So suppose that this is true. n A inverse is a subset of n for all A belongs to G. But you need to show that every right coset is a left coset, right? So then, what is n? So n can be written as n E. That is n A inverse A, right? That means n A inverse A, which is a subset of, now n A inverse is a subset of n, so it is Na. So an is a subset of Na. And if you take A inverse instead of A, then A inverse, just put it here. So A inverse n inverse of A inverse. So that must be a subset of n. But what is that? That is A inverse n A, subset of n. That is A inverse n is a subset of n A inverse. This implies, so Na equals to A inverse n A. Okay. So A inverse Na is a subset of n. So that means it is a subset of An. So in the previous case, it is An subset of Na, and in the second case, it is Na subset of An. And together, so combining these two, you have that An equals to Na for all A belongs to G. Every left coset, every right coset is a left coset. Okay. Now 4 implies 5. 4 implies 5. Okay. So let 4 holds. So what does it state? So 4 states that every right coset is a left coset. Every right coset is a left coset. Okay. Okay. So let A comma B belongs to G. Okay. Now An Bn. What is that? So that can be written as A Nbn. Okay. Okay. Now this is a right coset. But according to 4, every right coset is a left coset. That means Nb is actually some Cn or some C belongs to G. Nb equals to Cn. This is a left coset, a right coset, so it is equal to some left coset Cn. So that means it is AC Nn. But what is Nn? We have already seen that Nn is actually n, right? Okay. So it is ACN. Okay. So this shows that the product of two left coset is again a left coset. Okay. So 5 holds. Now 5 implies 6. What is 6? What does it state? Yeah. So 6 states that ANBN is going to be ABN. So this product will be actually ABN. But how? So suppose 5 holds. So let 5 holds. Then ANBN will going to be some left coset. Suppose CN. Okay. But we are going to prove that this is actually ABN. So AB can be written as A identity, B identity. That means A belongs to AN and B belongs to BN. But this product is actually CN. So AB equals to CN. So this implies AB is in ABN and also in CN. So it is in their intersection. So their intersection is not equal to phi. But we have proved that these left cosets are actually equivalence classes determined by the equivalence relation A is congruent to B modulo n with respect to the left relation, and being equivalence classes, any two equivalence classes are either distinct or disjoint. That means if they are not disjoint, that is if their intersection is not equal to phi, then they are identical. So for that case, so here ABN and CN are not disjoint because they have some common element. So for that reason, these two equivalence classes will be equal. And this proves that ANBN is going to be ABN. Okay. Now I would like to left 6 implies 7 as an exercise. As an exercise. Okay. Okay. And 7 implies 8. So let A and B be two elements. And suppose that A inverse B belongs to N. Then A inverse B belongs to N implies B equals to A inverse B. Okay. So since A inverse B belongs to N, so this element is in the left coset AN. Okay. And using this, identity can be written as E B B inverse, right? That means this E is in A N, B is in AN, and the rest is B inverse. So that means this is equal to NA NB inverse. Now by 7, you can write it as A N AB inverse. Okay. So that means this identity can be represented as an element of n AB inverse. That means E is actually some C AB inverse where C belongs to n. Okay? That means AB inverse is actually C inverse. Right? But what is C inverse? Being an element of a subgroup, C inverse is in n. So AB inverse belongs to n. So A inverse B belongs to n implies AB inverse belongs to n. In a similar way, just complete the proof on your own. If AB inverse belongs to n, then this implies A inverse B belongs to n. Okay? And this completes 7 implies 8. And the last one, that is 8 implies 1. And with this one, I would like to end this session. So 8 implies 1. So what we have to show, we need to show that n is a normal subgroup. That means every left coset is a right coset, or every right coset is a left coset. So let A belongs to any element of the group. Okay? Then you need to show that. So your goal is that n is going to be na. Okay? Okay? So then x belongs to na implies. So since x is in na, so x can be written as, so x A inverse must be in n with respect to the relation. That means x inverse A, it is in n, since being a subgroup. N being a subgroup, you can write this. X inverse belongs to n implies x inverse A belongs to n. And this implies A inverse x can be written as the inverse of x inverse A, right? So again, being a subgroup, it is in n. Okay? And with the help of this, so A inverse x belongs to n implies x belongs to n. And you can apply the same process by starting this step towards this one. That is, this implies this, implies this, implies this, and this. So hence, n is equal to na for all A belongs to G, and so n is normal in G. So this completes the proof. So I would like to end this session here. Okay.